Welcome to a lesson with Dr. Powell. We're going to talk about limits and continuity of functions. So you may have seen in the examples that we were having of finding instantaneous slope, what we were doing was we had some kind of expression like x squared representing a function here. And if we wanted to find out the instantaneous rate of change at a point, we did something like this. Difference of y values as x, and then a difference of x values from x to x plus h. So a run of h. And we simplified this down and we got something like x squared plus 2xh plus h squared minus x squared all over h. Okay. And then notice the x squareds cancel. You can factor out an h, 2x plus h all over h. And then notice that at this point, we wanted to see what happens to this quantity as h gets really small. But we can't plug in 0 because it's not defined. It's like there's a hole there in this expression, how it's defined for h. There's a hole, meaning it's not defined. So what we can do is we do some algebra until we get something that cancels so that we get an algebraic equivalence. It's not a function equivalence. This is an algebraic equivalence. Notice how domain has changed of h. So if x were like a constant and h were the variable in our function, think about what values of h that can go in here. H equals 0 does not work on this side, but it works great over here. That means that as a function of h, this side and this side are very different. However, algebraically, there's equivalence. So we got something that was algebraically equal to this, although functionally it's not. And then why is it not? Because there's different domains. So what we did is we changed the domain to something where we could actually plug this in and fill in that hole in a picture. It's kind of like we have some kind of expression and maybe it's not defined somewhere. But if we can algebraically do something so that we get an expression that actually has this defined, then we can fill it in. And we see what y value or what output value actually gets us there. This idea is called a limit. A hole fill. And we can think of it as hole filling. Now, if every single point on a curve is, if every single point on a curve itself is the actual point that fills in the curve to make it nice and continuous, we call that continuous. In other words, a function is continuous if I can take my pencil, at least this is an intuitive definition, and I can draw it without lifting up the pencil. We call that continuous. So a limit is a value, a y value, you could say, or an output value that would make a function continuous if the hole were filled in. And so that is what limits are, kind of an intuitive idea of them, and also continuity. Thanks for watching.